Hello, I'm Mark Unkefer. I'm Executive Director of the Fiber Optic Sensing Association, and welcome to our May webinar, Distributed Acoustic Sensing with Enhanced Fibers. And we have a very distinguished researcher from longstanding with OFS, Paul Westbrook. He has been with OFS for over 20 years and is a PhD from MIT in physics. So he is somebody with deep expertise in the subject matter. Paul, we look forward to hearing your presentation.
Thank you very much, Mark. So my name is Paul Westbrook, and I'm a technical manager at OFS Labs in Somerset, New Jersey. And I do want to thank the Fiber Optic Association for inviting OFS to give a webinar on the topic of distributed acoustic sensing with enhanced fibers. So I'll first give a little bit of background on distributed acoustic sensing. What is it? More broadly, what is distributed sensing? Then I'll talk more specifically about what distributed acoustic sensing is. And then I will discuss certain types of enhanced fibers, in particular ULL, or ultra low loss fiber, which is a fiber well known in telecom, but also very useful for sensing, and enhanced scatter fibers, or ESF, which can also be used for distributed acoustic sensing. Then I'll talk a little bit about how they increase signal to noise in acoustic systems, both the optical signal to noise and the acoustic signal to noise. Finally, I'll talk a little bit about some of the design considerations for fiber sensing links that would include these types of fibers. So distributed sensing applications generally involve the general field of structural health monitoring. So you have various kinds of large assets that needs some sort of monitoring of how they're doing day to day and how they're degrading over time. There are other types of applications such as security. You can see a fence over here, oil and gas installations, pipelines, you can see over here. Earthquake monitoring and various seismics, as I'll describe briefly, also are starting to become of interest for distributed acoustic sensing as well. Of course, telecom networks already have optical fibers in them, and they can definitely benefit from using those fibers to measure the health of the telecom network, as well as the health of assets that are around the telecom network. In general, the general field is really linear asset monitoring. So any kind of large, long asset can be monitored with optical fibers. So actually, Fiber Optic Sensing Association has put together a series of maps. You can visit their website and find out more about these. And you can see different kinds of places where optical fibers could be very useful. Pipelines is one of the key ones. This is rough amount of pipelines you have in the United States, and in principle, a large fraction of these could benefit from sensing along their length. So that's to give you an idea of the scale of these kind of linear assets that are out there. Obviously, pipelines have very sensitive aspects to them. They can leak. There can be security breaches and other aspects. You need to be monitoring their health over time. And sensing can have a really great impact on pipelines. This is a much bigger network. Roads have a lot more roads, and obviously not every road needs a sensor, but certainly roads that might be going through a tunnel or over a bridge could use sensing of various kinds. And there are often assets along roads, such as borderlands or other kinds of assets where you want to be able to do acoustic sensing. Another important set of linear connections are rail lines. Everybody knows that trains make an enormous amount of noise, and you can measure that noise easily with optical fibers and actually learn a surprisingly large amount about the health of trains and the tracks that they're on, as well as how fast the train is going and whether it's there in the first place, obviously. And lastly, of course, telecom. My company is obviously deeply involved in telecom optical fiber and cables. This is the network, not of actual fiber. So for people who think about fiber, 5 gigameters is not a huge amount of fiber. These are the actual connections. Those connections obviously can now be used not just for telecom, but for sensing. So I'll talk about how that can be combined a little bit later. So let's talk a little bit about what is distributed fiber sensing, in case you're not too familiar with this. What is the trick? What is the basic attribute of it? This is a cartoon of a distributed fiber sensor. The idea is that a length of fiber depicted over here, sort of snaking around, a source of light goes into that fiber, and the important thing is that fiber could be 1 kilometer long, it could be 100 kilometers long, and it can go deep into a mine shaft, or it could go under the ocean, anywhere you want. The source, once it goes into that fiber, the most important thing is that we'll also be talking about a lot, is that a little bit of light gets backscattered from every bit of the fiber. And that produces a sensing signal when it comes here to the detector, and also gets combined with certain attributes of the source. So what actually gets scattered back? There are both elastic and inelastic signals. The elastic signal is also known as Rayleigh scattering. It's essentially the same light that you put in, a little tiny bit of it is coming back. That light is all coherent. It shares the same phase as the source. And that's the main one we're going to be talking about for distributed acoustic sensing. There are, however, also inelastic contributions, Brio-on and Raman. And over here you can see what each of these is good for. The elastic signal, because it is rather large, can be used for acoustics. It can also measure strain and temperature along the fiber. Brio-on can be used to measure strain and temperature. And the Raman is good at primarily at measuring temperature. As I said, we're going to focus on the elastic scattering to measure acoustics. And in particular, we're going to talk about how we can measure the actual propagation of an acoustic wave over kilometers as it propagates next to an optical fiber. So now let me get a little bit deeper into distributed acoustic sensing. It has many names. There are many names. If you go into the literature, there are many names associated with this. Distributed acoustic sensing, or DAS, is one of them. Distributed vibration sensing is also appropriate, because really this is not like your ear. This is something that could be much lower frequency. It could be 100 hertz or a few hundred hertz. So vibration may be more appropriate. It also goes under the name of phase, or phi OTDR, and also it's known as coherent OTDR, where OTDR stands for optical time domain reflectometry. That is the method of sending the pulse into a fiber and collecting signal from every point along the fiber, where the time domain then separates out the different positions along the fiber. So I'm going to give one cartoon. It's not really a cartoon, it's really an actual realization of a distributed acoustic sensor, but it's really only one for illustrative purposes to show what are we talking about with coherent optical time domain reflectometry. I'll begin here with a very old picture from long ago, where a set of discrete reflectors was placed into an optical fiber, and my OTDR pulse was produced here from a laser array and sent into the set of discrete reflectors. Every one of these reflectors produces its own high back reflection. And the interference, the coherent or phase part of it, happens in this particular case in what is called a compensating interferometer, where the signal from the first Bragg grating is delayed so that it beats with the signal from the second Bragg grating. And that produces a phase sensitivity or length sensitivity between these two Bragg gratings. And that sensitivity can be extremely, extremely sensitive. Parts per billion change in the length of the fiber can actually be sensed using these kinds of phase techniques. Once again, this is only one type of method, but there are many other realizations of the same thing. But this is just to give you a general feel. Now, what has happened in the last 10 or 20 years is that it was realized that, in fact, you can just use continuous Rayleigh scattering. You don't need any Bragg gratings. You can just get rid of them. And you can determine with this distance here, which is called the gauge length, simply with your compensating interferometer or pulse width differences, or some digital signal processing in the detector. And if you work out the numbers, if you send in pulses at approximately 1 kilohertz, you can get snapshots of the phase of this fiber along its entire length. And you can, with roughly meter to 10 meter scale resolution, you can actually track an acoustic wave. Acoustic waves travel very fast in solid substances. They can travel 1 kilometer per second, much faster than in air. And you can actually get a plot of this sort where you see here time, which is this slow kilohertz rate, is plotted horizontally, and then vertically we have the distance. Every vertical line in this is one OTDR trace that was collected over time. And if we take the differences between those traces, we can then pick up an actual acoustic wavefront as it impinges on this fiber and literally squeezes this fiber. It causes a little tiny bit of squeezing, very, very, very small, which you can actually observe. Now, the important attribute that I want to point out is not the part where you see all these beautiful acoustic waves over here moving around. I want to talk more about this part over here where really nothing is supposed to be going on. That part is where we can assess how much noise there is in the system. And because we're using Rayleigh scattering, and in modern fibers, Rayleigh scattering is supposed to be very small, the signal you get back is really, really tiny. And that is going to limit how much signal you get. The amount of signal you get is absolutely crucial to picking out these kinds of acoustic and seismic signals that you have. So I'm going to talk about two kinds of fibers that can help you get more signal in your system. The first type of fiber is very well known in telecommunications. It's one of the primary goals of telecommunications to reduce attenuation of fiber so you can go further. But in sensing, that also helps a lot because in many cases, you want your sensor to go over very, very long lengths. And if you want to do that, these types of ULL or ultra low loss fibers, and here's a family, the TerraWave family of fibers, they can be have extremely low loss. The lowest typical losses you can get over very long lengths, that is 100 kilometer lengths, can be 0.155 dBs per kilometer. And that means that you can use your sensor further and further away from the interrogator pulse. And this is a formula that I'll discuss briefly later when we talk about some of the design constraints for sensor fiber links. But rather than just going with a lower attenuation, we can also just enhance the backscatter itself, just try to get more and more backscatter. And I need to show a bit of a cartoon of a fiber to show you how that works. Most of us think of an optical fiber as just a cladding, some sort of a cladding and a core. And the core has a larger refractive index. This larger refractive index guides light. But in reality, the core has very small refractive index perturbations, which result at a fundamental level from the fact that the fiber had to be drawn at a very high temperature. And those high temperature fluctuations are actually frozen into the fiber. Some of those fluctuations occur at a wavelength which is approximately equal to the wavelength of light in a fiber, which is typically on the order of 1 micron. So what we have when light propagates in the fiber, it doesn't just get to go in for free. A tiny bit of it at every single point along the fiber, I'm just showing one point, will scatter out of the fiber. And that produces a typical amount of attenuation, a kind of fundamental attenuation, which is a few % per kilometer. But a very small amount of that will be actually captured by the waveguide. So this acts like a source, and a little bit of it will get sent back into the waveguide. We categorize that with we quantify that with something called the capture fraction. And the amount of signal that therefore gets back reflected is, in this case, much, much, much smaller because the capture fraction is very tiny. So this light just leaves the fiber completely. The goal with enhanced scattering fiber is to produce a substantially larger amount of backscatter. So you can produce a factor of 10 or even 100 times more backscatter, say 0.1% or 1% per kilometer. Now you might say that 0.1% per kilometer is still very, very, very small. But if you're talking about a link which is 50 kilometers long, then 0.1% per kilometer is about all you can expect to have without completely depleting all the signal. So here's an actual coherent OTDR trace. Here you see the backscatter signal. It's a coherent backscatter signal, so it has a lot of fringes. Those fringes actually contain all the information. That's a reproducible speckle pattern of the scatter that is in your fiber. It's actually what you use to do the phase sensitive measurements. This is standard single mode fiber, which shows much less signal. And then when you use the enhanced scatter fiber, you have much greater signal. It does also have decay, but the signal can be much larger. So this is a 25 kilometer length followed by a 10 kilometer length. And we use a kind of figure of merit to categorize the backscatter signal. We essentially take backscatter and divide by the attenuation. For typical fibers, this number is approximately equal to 1. And for standard, for enhanced scattering fibers, it can be much bigger, factor of 10 or 100 larger than for a standard fiber. And that really is the basis for the enhanced scatter fibers. So OFS makes AcoustiSense, which is an enhanced scatter fiber. And this fiber, as you can see over here, on a very long length scale, has much larger backscatter. However, on a very short length scale, over here you see the fiber on only centimeter length scale, the enhanced backscatter is almost the same. It looks essentially like Rayleigh backscattering, and that means that there are no holes, there's no gaps, or at least no more holes or gaps than there would be with Rayleigh scattering. Here you can see the overall reflectivity from this type of enhanced scattering fiber. And an important aspect is that it's over a finite bandwidth, which can be controlled. And the area outside of it, the out of band region over here, is sufficiently low in backscatter that essentially it looks like regular fiber, except it has a little bit more attenuation. Importantly, when you treat fibers to produce enhanced backscatter, you have to do a stabilization anneal. And this over here shows that after such an anneal, even at 3 weeks, at 210 degrees Celsius, the fiber has virtually no change whatsoever. So such changes that produce increased backscatter over the Rayleigh scatter, which you see down here in blue, those can be actually quite stable over very long periods of time. The attenuation in the fiber is definitely a point of concern because whenever you treat a fiber to produce more backscatter or produce more perturbations, you can also increase attenuation. But here you can see that the amount of attenuation that you induce is similar to the amount that's already there, even at shorter wavelengths. And I show here the 1300 band because that's actually also useful in certain telecom applications. Over here, you can see the reflection versus approximately 1.5 kilometer length of the fiber. And this is the typical out-of-band scattering that you observe in such fibers. As I said, it should look like Rayleigh scattering. In fact, it does. It declines a little bit as you go through the fiber. However, in band, where the enhanced scattering is, you may start out with 13 dB in this case, but by the end of the fiber, in this case, we're actually even a few dB higher than that. So the enhanced scattering has gone up. And this is an important property of enhanced scattering fibers. It allows us to actually control how much scattering we get. And this is a particularly dramatic example of this counteracting attenuation. The blue line up here indicates a fiber with there was a little glitch in the middle here. This is a splice point between two fibers. And what you see here is some attenuation in a fiber that has an enhancement in it. This is the out of band attenuation. Over here you see the in-band attenuation and the in-band backscatter, which increases by a large amount. Now, this particular fiber was then exposed to hydrogen. If you're not familiar with hydrogen in optical fibers, hydrogen produces large amounts of excess attenuation in the fiber due to the formation of OH, due to molecular hydrogen and other effects of the short wavelength loss in fibers. And after treatment at 150 C with the hydrogen, in this particular case, the attenuation was 5 dBs per kilometer. So the green line here shows there's enormous attenuation, which really would cause the fiber not to be useful anymore. However, the backscatter signal, okay, because it was increasing when we started, is still in fact increasing after we're done with the after we're done with the hydrogen treatment. So this is a very dramatic example of how in an extremely harsh environment, an enhanced scatter fiber can continue to function as designed. Now, I've been talking about optical signal up to this point, but distributed acoustic sensing is really about acoustic signals. The optical signal is, of course, important, but we must show that it actually produces better acoustic signal to noise ratio. So really, we're going to go here from the optical to the acoustic signal to noise ratio. And here is a straightforward example of how this works. Here you see coherent OTDR traces from both the enhanced scatter fiber in blue and the standard single mode fiber over here. But here you see the acoustic signal. So this is the power of an acoustic signal versus frequency. And here, once again, the acoustics here is occurring at 1 kilohertz. So again, not super high frequency, fairly high in this case, but not super high. And the signal to noise ratio here is 29. You can see that you can actually observe the oscillations. And here the signal to noise ratio is 15 dB in the same fiber. This is the same sort of side-by-side comparison at the end of 2 kilometers of fiber. So you can see there's an enormous increase in the acoustic signal to noise ratio. Now it's also important using distributed acoustic sensing to recover the actual phase. In the most sophisticated systems, you want the actual phase or the actual length change of a piece of fiber. And one way to do that is to actually take your fiber and put it on a spool, which can expand using piezo electrics and make very small changes in very long lengths of fiber. So in this case, we have a PZT exciter with 15 meters of fiber, and the PZT exciter then causes the fiber to expand in length by a very small amount with a very controlled signal. This controlled source was put at the end of 40 kilometers of standard single mode fiber. G652 is standard step index fiber, well-known step index fiber used in telecom. And this particular fiber had approximately 24 dB attenuation going in and out. Here's your DAS source and the detector. So first what we did is just put standard single mode fiber on the end of this. In the standard single mode fiber, the G652 style fiber, it was almost impossible to recover the phase. This is the actual phase here versus time in seconds. However, when we put the enhanced scattering fiber, we are able to completely recover, under the same conditions, completely recover the signal that we observed. And in this case, if you quantify what you have, there's almost a factor of 1,000 increase in signal to noise. So the scattering fiber in this is really truly enabling the distributed acoustic sensing at this large range of approximately 40 kilometers. Now, it's also important for fibers to be placed into cables or other structures so that you can put them in the application. And OFS has produced what you see down here, a simplex cable. That is a cable that has a single fiber inside with fairly standard packaging that you can see over here. This fiber, this particular cable had both standard single mode fiber and enhanced scattering fiber. And the cable, as you can see here, was placed inside an acoustically isolated area, and then a speaker was put inside to get a fairly controlled acoustic signal that could be applied to both the standard single mode fiber and the acoustically sensitive fiber. And that acoustic signal was actually was put at multiple frequencies, 50, 100, all the way up to 450 hertz. Notice this is an acoustic frequency scale over here, and we can see a signal that shows up at multiple different frequencies over here, well above the noise for the AcoustiSense enhanced scatter fiber. However, here, if you use the telecom grade, the standard single mode fiber that's in the exact same condition, the same cable and the same box, we have much, much lower levels of signal. And in fact, the acoustic signal to noise is 7 dB higher when you use the acoustically sensitive, the AcoustiSense style cable in this. So once again, a demonstration that extra optical signal actually is producing more acoustic signal in this particular environment. Now, another very important area where sensors are used is in combination with fiber and metal tube. This is a technology that allows fibers to go in very harsh environments. And OFS worked with NVG and their Somerset fiber and metal tube technology to produce 2 different types, solid and perforated FIMT, and to produce, again, side-by-side comparisons, not only with the different types of fibers, standard fibers, and the perforated FIMT, standard and enhanced scattering fiber, but also with solid and perforated FIMT. And over here, you see the Somerset in general is better. The red curves are always better, so it allows that acoustic signal to get inside. But an even larger signal that you observe is that in all cases, the enhanced scattering fiber produces more signal throughout. So this is a case where the fiber once again has been packaged, and it shows better acoustic signal. Now, I also want to talk about telecom systems. Once again, OFS provides many different fibers for telecom applications. And this is an example of how an enhanced scattering fiber can be installed in a telecom system. Over here, you can see an actual fiber sensing system here, which was installed and sent into an actual field fiber. This was in a part of New Jersey along the Jersey coastline. There's about 38 kilometers that goes into a buried cable, and then near a cable on a fence, and then a cable that's in a pole. And the idea was to then put many different stimuli, such as somebody walking near the fence or the pole, and to see what was the difference between the standard fiber and the enhanced scattering fiber. And here you can see that the signal to noise is substantially higher in the enhanced fiber than it is the standard single mode fiber. And I just blow up over here one of the figures, which shows down here with the enhanced fiber, somebody walking near the fiber. They're walking over on this path or jumping over here. And you can actually distinguish walking from jumping very easily over here. Whereas in the standard fiber, in this application, really it's kind of impossible to see anything. So this particular result is truly enabling for kind of security type application. It shows you that at some distance, 38 kilometers in this case, you have a total ability to recover signals, meaningful signals, in a kind of security perimeter setting. Of course, you can recognize, you can even recognize, for instance, walking from jumping in this case. I also want to bring up another area that has become very interesting in recent years. It's been realized that optical fibers using distributed acoustic sensing can actually be used to detect earthquakes, to detect seismic events. And recently, a group, Norsar in Norway, has actually, they already have seismic arrays, standard seismic arrays, and they have a long history of using those for earthquake detection, other applications. But they have now installed a fiber seismic array. This is a picture of that seismic array. This kind of star-shaped structure is approximately 3 kilometers across, and it has optical fibers going out in the different directions. The reason that it's a star shape is so that it can measure ground motions in all different directions as they pass through this region. And Norsar, it's a very interesting platform because they have the same seismic array in this area as well. They have seismometers, traditional seismometers, all over the same structure. This has only recently come online. This is some of the data that was taken, and some of the enhanced fibers, enhanced scattering fibers are also installed in this structure. And down here you see actually the tragic Turkish earthquake of 23 was observed. Obviously, that's a rather large signal, and there would be obviously interested, if you ever looked at seismometers, you will know that there are earthquakes going on essentially all the time, small and large, and so that this signal would be much bigger than smaller everyday earthquakes. And the real question is how far such a fiber structure can go to improving our ability to measure that. Now let me talk a little bit about sensor link design. We have recently gone through the process at OFS of trying to understand some of the limitations that enhanced scattering fiber would have. So we wanted to be somewhat agnostic about the particular type of interrogation scheme and only ask what kind of an E field do I get returned from a particular scattering fiber. So I'll remind you over here, this is the return loss, otherwise known as the reflectivity, the overall reflectivity in this case from a scattering fiber. In band, we have some large amount of scattering that's, an order of magnitude or so larger than the Rayleigh scattering, and out of band, we have essentially Rayleigh scattering up here. The black one is essentially just that's a standard fiber. So let me direct you first to the two bottom curves here. which describe the effect of attenuation in the fiber. So what I have plotted over here is the signal, dB, and the black line indicates the amount of returned signal that you get as a function of position in the fiber. Here we're going out 40 kilometers or so in the fiber. The amount of signal that you get returned just decreases linearly on this log scale over here, and until you hit a kind of minimum level, a certain amount of signal has to come back, otherwise the distributed acoustic sensing won't work anymore. The enhanced fiber has this RE, R sub E, which is measured here in dBs, which tells you how much more backscatter you get. That RE from this plot translates into an arrow over here, which is at 0, at the 0 position. You start out with more signal, factor of 10 or whatever, 10 or 100 more signal. Typically, the enhanced fiber, though, will have more attenuation, a little bit more or perhaps a lot more attenuation, and therefore it has a steeper slope. And in this particular example, we can see that we have, that is compensated for by the enhanced scattering, so that we have a bigger sensor reach. So we reach the signal, the minimum signal at a further distance out. Now up on top here, I'm showing another effect, which we're calling MPI. It's also known as crosstalk. And I'm talking about that in terms of the signal to noise. This is the signal to noise for MPI. And that's essentially the amount of single scatter. That's the useful one. Single scatter within a fiber is useful, divided by the MPI, which is everything other than the single scatter. So ideally, we don't want any non-single scatter. We don't want the light just rattling around in the fiber and bouncing many, many times. We only want a single backscatter. So we want that signal to noise from the crosstalk or multipath interference, MPI. We want that to be above a certain level. And I put that here at a rough number. 15 dB, could be other values depending on the interrogator, maybe 10 dB, maybe 20. But I just chose 15 over here for this. The black line, once again, shows what happens in a standard single mode fiber. The line is this logarithmic approximation, and these are actual simulations that we've performed using the model described down here. Now, once you put in the enhanced backscatter, in this case, the metric actually goes down. This entire curve is pushed down by the exact same amount, but that curve was pushed up, and it remains lower the entire time through because in this particular approximation, attenuation does not affect MPI. So there's an MPI limit here, kind of MPI reach, that is also reached when there's so much MPI at a certain point that you can't see the signals anymore. So these are considerations that have to be taken into account. They do depend on the type of interrogator and the requirements on the interrogator. So this is not a commentary on any interrogator. This is just the physics, essentially, of what happens with an optical fiber with enhanced backscattering. Now, one simple thing to do is reach extension. You have standard single mode fiber and simply put an enhanced scattering fiber after it. So here's the standard fiber. Its MPI, as we said, goes down slowly, logarithmically, and the signal goes down linearly here on this dB scale. At some point, you have no signal left. At that point, you place an enhanced scatter fiber in. Suddenly, the signal is restored, but it also will then decline, and then you have the combined reach of both. Notice that the crosstalk actually improves a little bit because we have more signal over here, but the crosstalk is dominated by the end of the fiber. So in fact, you have improved crosstalk briefly, and then it declines again. So in this case, it's entirely power limited. And here's this reach extension that you have. Here's an actual real world example where we're going to combine sort of all the fibers we've been talking about. This was a case where the ultra low loss fiber was used in combination with standard single mode fiber and the enhanced scattering fiber. So here's a DAS box that was hooked up to TeraWave ULL, and in this case it was 100 kilometers of fiber, longer than the typical length used for most DAS boxes. Then a certain amount of standard single mode fiber, which has more backscatter than the ULL, so it produces signal. And then lastly, a bit of enhanced scattering fiber, in this case 1 kilometer. What you see down here is the last approximately 1 kilometer of fiber, which would be the enhanced scattering fiber. And this blue area is relatively low noise that you have in that entire enhanced scattering fiber because the signal has been completely recovered. Then the last little bit of fiber, an acoustic signal, was applied. And you can see that acoustic signal over here as it's being detected. So once again, this is the actual length over here, not the entire length, only the last kilometer. And here is a time span in 60 seconds. So it's a relatively low stimulus. Further reach is also possible beyond this level. The last thing I would like to say is that, once again, obviously telecom, in telecom there are many fibers that are already there, and their main purpose, obviously, their main revenue generation comes from telecom. So there is a general question of whether you can do sensing and telecom in the same fiber. Obviously, if the fiber has no sensing, no enhanced scattering or anything in it, it should be possible. But if you have a link of this type, you would like to know whether the enhanced scattering fiber will disrupt the actual sensing capabilities. So here's a case where a coherent transmitter was sent into, once again, the ULL fiber, the TeraWave ULL fiber. In this case, it was 100 kilometers. And then that was sent to the enhanced scattering fiber just to see if you can do telecom. So signals were sent both within the band. Over here you see the bandwidth. In this case, the bandwidth was chosen to have different amounts of backscattering so that we could probe different levels. Here you can see as much as 24 dB, more than a factor of 100 increase in backscattering. And then out here it's very low, almost none in these parts. And here you can see the backscattering fiber. In this case, it was 10 kilometers long, and there's the actual enhancement measured on just a conventional OTDR. And the main point here is that there's really very little penalty of signals that are outside. This is the OSNR penalty. OSNR penalty is plotted here on this axis. And when that OSNR penalty is below half a dB or so, it means essentially that there's nothing happening. So you can get fairly close to the actual bandwidth of this fiber and see signals. Within, of course, you do have some penalty, very large amounts of backscattering. That's well known that such things can happen if you have too much reflectivity, distributed reflectivity. But this shows that it is really a possibility that scattering fiber can coexist with telecom signals. So in conclusion, I think I've shown you that distributed acoustic sensing, this method of turning an optical fiber into a gigantic microphone, can benefit greatly from enhanced fibers. So here, once again, is that dramatic example where a person walking next to a fiber is visible with the enhanced scattering fiber down here, and it's really, you can't make any interpretation with the standard signal mode fiber. So that enhanced scattering fiber really acts as a much better microphone at these long distances, because signals have been increased by a factor of 10 or more. And I've shown you how you can actually counteract attenuation, particularly in harsh environments. We've also talked about ultra low loss fiber, which is very useful in telecom, but also for sensing, to extend sensing range. And I want to point out that there's no specialized amplification or special interrogation techniques that are required. Even the lowest grade interrogators, the lowest cost interrogators can be used with this type of fiber, and no specialized extra amplification of any sort, Raman or any other thing, is required to get these kinds of results. And I think I've shown you that enhanced fibers can be designed into many different types of distributed sensing applications, harsh applications, telecom, long reach, and many others. So we do anticipate that there will be increasing interest in this sort of fiber to be able to do acoustics within a system in a manner that doesn't even interrupt the telecom signals. And with that, I can take any questions.
Well, thank you very much for a very fascinating presentation. We've already have a number of questions, but I really did want to kind of start with a focus on a couple of issues. With we've heard from basically, I guess I would cluster them around the changing economics for fiber optic sensing generally. As I understand it, you have the capacity to have fewer interrogators or interrogators over longer distances. And obviously that's very significant. So one question is, have there been any commercial uses that, or are we still essentially with the fiber in the more experimental stage and have yet to see it in real application?
Yeah, generally the enhanced scattering fibers, the main area where they have the greatest value at this point is in seismic and also sort of health monitoring in oil and gas facilities. So there's a premium on getting additional signal because such systems typically will have attenuation of various kinds in the system. Enhanced scattering fibers are quite valuable in that setting. In the wider setting, there's still a lot of wider setting of different types of security, telecom, and these other areas. I think there's still a lot of exploration as to where it's fitting.
So we're, to put it in a positive light, kind of early stages in kind of the development of that. So let me just follow up then with that, which is how can OFS help customers design the best distributed sensing system, really taking full advantage of the capacity that the enhanced fiber has?
Yeah, so I think it's a good question. What I've tried to show in the talk here is that at OFS, there has been an emphasis on looking at the basics, the fundamentals of fiber fabrication and making various kinds of low loss and enhanced fibers on the one hand, and tailoring those to whatever a customer needs as to the amount of enhancement or the amount of attenuation or the bandwidth where you may want enhancement, be it at 1300 or 1550. And also then producing cables. So OFS produces cables, specialty cables, telecom-based cables, and combining all of that together into a complete package. We also do extensive testing. Some of the testing you saw was done at OFS to test the capabilities of various kinds of interrogators. So really OFS can bring in the actual recommendation for how the different types of fiber should be used in distributed acoustic sensing and actually verify and test that can happen. So we can truly work with somebody who's really getting, trying to get into this and doesn't fully know exactly how they should be doing it. We can give you kind of all the pointers you need to build up an appropriate and optimized sort of sensing network.
So having extended the limits, the natural question then is, what are the limits of current fiber optic acoustic sensing, and how can enhanced fiber extend those limits?
Yeah, I think so. The key thing about this, there's sort of two kinds of limitations. The first one that I described to some degree is reach. So there's always a point at which you can no longer get signal. And definitely the enhanced scattering fiber will produce improved reach. More importantly, though, it's possible to extend the interrogation capability. So interrogators generally they're specified and they're designed to function with Rayleigh scattering, with weak Rayleigh scattering signals. However, when such interrogators are used with more scattering signal, you can change the parameters. You can change spatial resolution, you can change acquisition speed, averaging times, and push the system into regimes where you're measuring signals more quickly, you're getting more dynamics, and you're getting better spatial resolution. So that area, I think, has not been fully explored. And as we get further along, we're going to start seeing cases where an enhanced scattering fiber will truly enable, as I showed, a situation where, for instance, a person walking next to a pipeline or a backhoe that's operating near a pipeline, it's buried perhaps, it may be completely invisible for a standard fiber. But as I showed, the enhanced scattering fibers simply have a larger range where they can actually measure what's happening. So that sort of fiber can have actual acoustic, sort of better acoustic range, in addition to better optical sensor range.
So if I'm hearing you correctly, I guess one of the things you're saying is that it's potential for the algorithm, the software on the essentially on the interrogator side to be that much more sensitive to be able to filter out the false positives by being more specific of identifying more precisely particular events of interest. I guess that's kind of the core of what you're saying.
Yeah, I mean, it's essentially as I was showing, the acoustic signal to noise is better. And many of the sort of modern machine learning and artificial intelligence techniques, many of them boil down to denoising. They're essentially trying to use AI to produce a real signal from noise. However, if you begin with less noise, if you have less noise to start with, the denoising works better. And moreover, if you have the same denoising capabilities, and if you have the same kind of sophisticated interrogator, you will now be able to measure signals that are 10 times weaker. So you measure earthquakes that are 10 times weaker. You can measure structural problems or things that are much, much smaller. So that's really it's in some sense, it's a signal to noise issue. You can just hear much, much better. And all of what you've done before now works a lot better. Could be 10 times or even 100 times better.
Now, have you given thoughts of using this enhanced sensitivity to expand the potential applications for sensing? Obviously, right now we're very focused on sort of long linear assets that need some level of security. Do you envision some other applications that might be opened up as a result of the fiber?
Yeah, I think there are a number of possibilities. Certainly, it is, though, constrained. At some level, you do need something that's long, and because once you get short lengths, there are many different applications. For instance, seismometers are single point sensors. But within that sort of linear space, there are a number of kind of harsh environment areas, in oil and gas and in nuclear sites and other areas where, in principle, such sensing can happen. And obviously, in telecom, in different areas of telecom, because there's so much fiber there already, this sort of combination of telecom with sensing, I think, is an area that I think, perhaps not at the moment, but in the future, it will become obvious that it's quite useful to be able to monitor within a telecom network and a much broader range of applications what's going on sort of acoustically near telecom infrastructure and near the infrastructure that it's inside the infrastructure where the telecom has been installed. So I think there should be a large number of possibilities once people see the capabilities that such fibers have.
Now, clearly, one of the challenges is it's a greenfield. This is a greenfield application in that you need to put in new fiber. That said, many fiber optic sensing applications do, in fact, involve greenfield because of concerns about construction and building near an asset that may make people more reluctant to change the existing fiber. Greenfield has been more prevalent around the world where new infrastructure is being installed as opposed to in the United States. So do you see this as being a kind of global advantage where you do have fresh infrastructure going in and you have greenfield and they're able to take advantage of this capacity?
Yeah, well, certainly, I mean, OFS is part of the Furukawa group of companies, and these companies it's a worldwide. We're in Europe, in Brazil, Japan. We're in throughout the world, and definitely this sort of these sort of sensing applications. The whole group of companies is looking at all the different possibilities around the world, and certainly greenfield is one of the main places where you would see this. It's a very forward-looking technology. What you're thinking about is future-proofing, sensor future-proofing your infrastructure as it goes in. So But as more and more infrastructure is put in, which certainly will happen, we anticipate that this sort of fiber will take hold in many more places. I should add that it's, even in places where there's legacy fiber, in many cases what you're seeing is that you have a legacy fiber that's there 30 kilometers or 40 kilometers, and you want to extend it. So you want to get sensing to happen somewhere far away. And if you add kind of brownfield, add a bit of this enhanced scattering fiber out far into the field, you'll be able to actually use it. So you can sort of bring areas to life that don't actually have sensing fiber currently. So that kind of extension is another area that's certainly a possibility.
Well, we have a number of questions from folks who've asked when the presentation, or will the presentation be available in the future? And of course, the answer is will be available on FOSA's YouTube page, and it stays there for a long time. But we have the presentations up there from the very beginning. So for those who are still kind of digesting a lot of this, and there's actually a lot to digest in this presentation, it will be available on YouTube. Also, your contact information is available, so folks can contact can contact OFS and learn more information about that. But we thank you very much for a very thought-provoking webinar. There's a lot of very good information. And that concludes our webinar.
Thank you very much.